Good morning, friends. Now we are discussing the various heat treatment processes uh, in the material testing lab. So, aim of this experiment is to study the various heat treatment processes. It is a demonstration experiment. So, here heat treatment is considered as an operation, or it is the combination of operations so that alternate heating and cooling of the metal in the solid phase will be carried out, so that certain required properties will be obtained for the given metal. So heating the metal and cooling the metal in the solid phase will make the metal to acquire the required properties. So here the ferrous materials will be heated to the above transformation temperature. So and it will be heat treated to obtain the different structure. So what type of heat treatment is to be given is based on heating the material to certain temperature, and we are employing different cooling rates. So in this process, heating temperature and the rate of cooling adopted will play an important role. To what extent the given specimen is heated and what is the rate of cooling adopted. So it plays the important role in different heat treatment processes. We have the classification of heat treatment processes like this: annealing. So it is primarily the process of heating the metal so that the metal which is a distorted structural state. So this distorted structural state will be stabilized by heating the metal to a temperature, so that the increased temperature will remove the distortion, and then the metal will be cooled down to the room temperature, so that the structure, metallic structure, will become stable. Then normalizing. So this is the process where heating the metal above the transformation temperature up to 900 degrees centigrade and cooling from that temperature. Then hardening. So hardening is performed on the metal so to get the required hardness and the structure. So this hardening process involves heating the metal above the transformation temperature, that is around 900 degrees centigrade, then holding this temperature for 15 to 30 minutes for 25 mm of cross section, and then quenching it immediately in a suitable cold medium like water, oil, etc. Then tempering. So here hardening process of the metal will produce the martensite structure with some retained austenite. So this martensite structure will make the metal very hard and brittle. The retained austenite is unstable and it is going to change with the time. So this transformation of retained austenite at room temperature will lead to the distortion of metal. So we cannot use this hardened metal as it is because of this changing austenite structure. So hence tempering will be carried out on the metals.
Welcome to Tools and Process, a new series of short videos in which I will talk about the tools I use and my process for accomplishing certain goals. Today, I will cover some aspects of heat treating. Heat treating is the process of hardening carbon steel to specific hardness. It requires heat and controlled cooling of the steel. My heat source for long swords is an even heat KF45 electric kiln. For smaller knives, I normally use the forge to bring the steel up to critical temperature. As preparation, I remove all vertical grinder marks from swords by draw filing. Another important tip is that the sword needs to be on its edge instead of lying on the floor. Putting the sword on the floor of the kiln leads to uneven heating and warping of the blade. Since my high carbon steel is 1075, I programmed the Ramp Master to bring the temperature to 1500 Fahrenheit, that's 815 Celsius, and hold it there for 6 minutes. To find the critical temperature of high carbon steels, you need to refer to a table that you can often find on the internet. Curiously, when searching for 1075, you will find at least 4 different temperatures, and 3 of them are completely wrong. The first step in my heat treating regime is to normalize the blade. Since steel is in crystal form, the repeated heating in the forge causes the steel to form larger and larger grains that make it brittle. Slowly cooling it down from its critical temperature reduces the size of these grains. This is also a good opportunity to check for warping, which may occur when the bevels have been ground unevenly. I was also hoping to show you some recalcitrance, which happens right when the carbon in the iron matrix transitions from austenite to ferrite. That transition releases visible heat. You have to check my spear video, where you can see that clearly. Here, I unfortunately stepped into the video. The next step after normalizing is hardening the blade. Steel can only be hardened when it has enough carbon content. Generally, the more carbon, the harder you can make the steel. As I had mentioned before, the steel is a crystal form, and the position of the carbon in the iron matrix determines the hardness of the steel. There are 3 carbon arrangements you should be aware of: ferrite, which is soft, martensite, which is hard, and austenite, which is the carbon arrangement when the steel is at critical temperature. When working with pattern welded steel, the pattern becomes visible under heat due to color differences and oxidization, as you can see for the sword here. Now it's time to heat the blade back up to critical temperature and then quench it quickly in a high-speed quenching oil. The oil will cool the blade down rapidly and cause the austenite to convert to the hard martensite. When quenching in oil, I always wear full face protection. If the oil gets too hot, it can rapidly ignite and flames can spurt up into your face. Before quenching the blade, I quickly check it with a magnet to verify that it is no longer magnetic. When I insert the blade, I also move it up and down vertically to prevent a rapid transition of hardness in the tang. Coming back to the quenching oil, I'm using Parks 50, which is a high flash point, and my quenching tank is also large enough so that the whole tank does not become too hot. Other oils with lower flash points are much more dangerous to use, so be careful. After quenching, the blade is brittle, but the pattern so much more visible. If the blade has been ground unevenly, heated unevenly, or quenched unevenly, it may develop a warp and as a result may no longer be straight. However, I will show you a trick that you can use during tempering to straighten the blade. Before we go there, let's quickly check the hardness with a file. On the hard part of the blade, the file will skid, and on the unhardened parts it will bite. In this particular case, I think the blade could have been harder and I should have requenched it. However, if you listen to the noise the file is making, you will hear that it somewhat skids on the blade but bites on the tang.
Thank you, friends.